So let's get settled in. We want to get started with the session. I think we're already about 5 minutes over. So I'll let Sridhar introduce himself and then we can get started.
Good morning, everyone. My name is Sridhar and I work for Hat.
My name is Daya Kamath. I'm from Ericsson, principal engineer there, and I work primarily on the network project that Anil has mentioned in his previous presentation, focusing on a wide variety of features in that project.
So one thing we'd like to mention is that the questions are not just at the end. So if you have any questions, you can interrupt us as we speak. So please raise your hand so that we can take your questions. In case if you feel that the question actually requires more time, or probably if it's slightly out of the context, we can always take it at the end or maybe after the session. So let's start with the agenda. So we'll be briefly covering about some introduction on IPv6, covering neighbor discovery protocol, then going into the neutron IPv6 support, like particularly from an API point of view, how it's supported. Then Daya will be covering IPv6 support in ODL Boron as well as carbon cycle, how it's implemented, its basic design, and some of the security group stuff and so on. We'll finally conclude with some snapshot on the basic use cases that we are currently supporting, and we'll finally have the roadmap stuff. So this is a slide that shows the IPv6 header. So IPv6 is not just about having a larger address space, but it's actually a protocol that is designed to be more efficient and more optimal. So the basic IPv6 header is of about 40 bytes. One noticeable difference that you can see here is that the number of fields between the IPv4 header as well as IPv6 header is, in IPv6 you'll find less number of fields. And one very visible one is that you don't see a checksum. So the main reason behind actually choosing less number of fields here is to have a more efficient processing by the intermediate routers and also on the nodes. So the fixed header is of 40 bytes, there's no checksum field, and so on. Although the number of fields have been reduced in the header, what it actually has is an optional extension header. So the optional extension header is used on a need basis, and in most of the cases, only the fixed header is used. There are some optional headers like hop-by-hop extension header, routing header, fragmentation header, and so on. So whenever there's a need to fragment a packet, that's when the fragmentation header comes into picture. So that follows the IPv6 header. So the next header field will be pointing to the fragment header and so on. There are three basic types of IPv6 addresses. The first one being the unicast address. It's actually an address that is assigned to a single interface. Any packet that is destined to that particular address is delivered to the corresponding interface. Multicast addresses, on the other hand, are very similar to the multicast IPv4 addresses. They represent an IPv6 multicast group. Hosts that are interested in receiving packets destined to that multicast group can join the multicast group, and the routers will make sure that packets coming to that group are forwarded accordingly. We have a third kind of address that is known as the anycast address. This looks very similar to the unicast address, with a slight difference that it's not assigned on a single interface, rather it is assigned on multiple interfaces and usually on different nodes. So when a router has to forward a packet to an anycast address, it looks into its routing table and then looks at the nearest interface to which that packet has to be delivered. Although we have these anycast addresses in IPv6, it's still kind of an experimental stage, and it's not kind of widely deployed. So you can see that we don't have a broadcast address in IPv6. So broadcasting is completely eliminated, and wherever they need broadcasting, they kind of use multicast extensively. So even within the unicast addresses, we have different types. The first one is, let's say, the global unicast address, that is like public IPv4 address. Then we have the link local addresses, which are addresses that are used within the local network. We also have unique local addresses, which are like private addresses in IPv4. Let's talk about the global unicast address, because the focus of our presentation is mostly on the IPAM use cases. A 128-bit IPv6 address consists of two things. One is the subnet prefix, and the other one is the interface ID. Subnet prefix is usually 64 bits, and the interface ID is 64 bits. Usually, the best practices dictate that you should use a /64 prefix on the end hosts or VMs. However, on the networking gear like routers and all, you can have a smaller interface ID for some security reasons. So with this 128-bit address, which is split into subnet prefix as well as interface ID, the subnet prefix itself can be divided into two. When you get a prefix from your ISP or a service provider, he can normally provide you a /48 or let's say /56. During the initial days of IPv6 adoption, they used to give a /48 prefix. Now, when you have a /48 prefix, that leaves you with a 16-bit subnet ID. When you have a 16-bit subnet ID, it's like 2 power 16, that is 64K different subnets. So as an end user, when you receive a global routing prefix of /48, you are allowed to have 64K different networks or subnets in your home. They felt that maybe this is kind of redundant and then reduced it to /56. So moving on, here we'll be talking about the neighbor discovery protocol. ICMPv6 plays an important role for neighbor discovery. It is primarily used for some of the use cases like address resolution, duplicate address detection, router discovery, neighbor unreachability detection, and so on. So what is router solicitation? There are basically 5 different packets when it comes to neighbor discovery. The first one is router solicitation. When a host actually comes up and it wants to acquire an IPv6 address using auto configuration, it sends out a router solicitation to see if there is any IPv6 router in the network. The response to this router solicitation is the router advertisement, and that comes from the IPv6 router. So what the router does is it periodically sends out router advertisements, and sometimes on demand basis, when there is a router solicitation request coming from VM, it immediately transmits a router advertisement. It is this particular packet that actually has very important information, like it has the prefix length, default gateway, MTU, and so on. So VMs or the host, after receiving this router advertisement, will know what kind of addressing they have to use on the network, and then they act accordingly. We'll be talking more about that in the next few slides. Then comes the neighbor solicitation. So in IPv4, we all know that we have ARP. So whenever a host wants to know the layer 2 MAC address of an IP address, so it sends out an ARP broadcast. The equivalent thing in IPv6 is the neighbor discovery. So neighbor discovery is a packet that is sent out on the network to get the layer 2 MAC address. The only difference here is that we use ICMPv6 for that, and it's not a broadcast. It's actually a multicast. So we spoke about unicast addresses, and we said that a packet that is delivered to destined to unicast address is delivered to the corresponding interface. So when a host has a unicast address configured on its interface, the host is not only going to receive the packets destined to the unicast, but also packets destined to the solicited node multicast address. So every unicast address also has a corresponding solicited node multicast address. So the host joins the corresponding multicast group, and it starts receiving those packets. So the neighbor solicitation packets are not broadcasted, but they are kind of sent to that multicast group, so that only that particular host will actually be receiving those packets, and assuming that it has the unicast address configured, it will respond back. The response to the neighbor solicitation is the neighbor advertisement that gives information about the MAC address corresponding to the v6 address. The last one in this sequence is the redirect message. Redirect is very similar to the redirect message what we have in IPv4. So if a router feels that there's a better first hop to reach a particular destination, it responds back with an ICMP v6 redirect message. So we talked about the global unicast address previously, and apart from statically configuring an IPv6 address on an interface, we have different ways in which a host can acquire a v6 address. One of the widely and most used addressing schemes in IPv6 is called as auto addressing, or IPv6 SLAC. It stands for stateless address auto configuration. So what it does is it allows an IPv6 compliant node to autonomously generate a global IPv6 address based on the prefix that is obtained from the router and with some local information, it computes the interface ID and then configures this address on its interface. Just like how we have the DHCPv4 in IPv4, we have DHCPv6 support in IPv6 as well. Within DHCP, there are two things. One is DHCPv6 stateless as well as stateful. DHCPv6 stateless support is kind of used when the router wants the VM to contact the DHCPv6 server for other information like DNS and so on, while using the router prefix for auto address configuration. The last mode, which is DHCPv6 stateful support, is like, the entire IPv6 addressing as well as the other information is obtained from the DHCPv6 server itself. So irrespective of all the modes, whether it is Slack or DHCP, a router advertisement plays an important role in the whole of this auto addressing mechanism, primarily for the following reasons. First of all, it is a router advertisement that is going to inform the host about the kind of addressing that needs to be used on the network. Second thing, the router advertisement carries the default route that has to be used on the interface. Third one is the MTU information, which is very important in case of IPv6 because of path MTU discovery and so on. There's no fragmentation, by the way. Routers are not expected to fragment any packets. So path MTU information is advertised in router advertisement, and even when you're using the DHCPv6 stateful support, the prefix length is obtained in the array, even though the address is obtained from DHCPv6 server. Let's take a use case and how a VM acquires an IPv6 address when it comes up. So I'm not sure how clean it is, okay, how visible it is, okay. Now, onto your left, you can see a VM, and onto your right, you find an IPv6 router. Assuming that the VM has IPv6 built in, which by the way is kind of, default nowadays. Most of the modern operating systems have IPv6 built in. So the very first thing that it does is it generates a link local address using the MAC address plus a well-defined link local address prefix, which is FE80 with a prefix length of 10. And it marks this address as tentative. After marking this address as tentative, IPv6 sequence actually goes through something called as a duplicate address detection. This duplicate address detection is performed for any address that is configured on the interface, whether it is link local address or any other global unique address and so on. So duplicate address detection is a process or a mechanism in which a host tries to see if there is any other host in the network that is already using that particular address. In case if it's already being used, then it doesn't proceed and configure it, and when it does not get any response, that's when it configures the address on its interface and starts using it. So how duplicate address detection works is by sending out neighbor solicitation. At this stage, in step number 2, you'll notice that the VM still does not have any v6 address on it. So the source address of the packet is used as like unspecified source, which is represented using 2 colons. And again, this is sent to the solicited node multicast address of the link layer address. Okay. Assuming that there is no host with the same address, step number 3, the timer that is actually started in step number 2 actually expires. There's no NA that is received. So the link local address that is now configured as tentative in step 1 moves to preferred state. The next important step that actually is required is to see if there is a router in the network, and for that it actually sends out a router solicitation request from the link local address that it just configures on its interface, and that is sent to well-defined all router multicast address. So all router multicast address is like FF02:2. So there are some well-defined multicast addresses in IPv6, and now this particular address is an all router multicast address. So what it means is when you have an IPv6 router, the router is expected to listen on this address. All router solicitation packets are received by not just one router, because there's quite possibility to have multiple IPv6 routers in your network. So the router, after receiving this packet, would frame a router advertisement in step number 5 and then respond back. The router advertisement actually has important information like certain flags that would help the VM or the host to know what kind of addressing it has to use. I will just talk about few flags here. The first one is the managed flag, which is represented with M. So when you have this managed flag set in router advertisement, what it implies is that this particular network will be using DHCPv6 services. So the host is expected to start the DHCPv6 client, talk to the DHCPv6 server to acquire the IPv6 address. Now, in this particular use case, we are talking about Slack. So both M and O, where O stands for DHCPv6 stateless mode, sorry. By the way, O stands for other information like DNS. So here in this use case, both M and O would be turned off, whereas A, auto-addressing flag, would be turned on. So it implies that the VM should actually use the prefix that is advertised as part of router advertisement and configure that on its interface. Now, how does it do it is like in step number 6, it takes the prefix and the prefix length and then computes the interface ID that we discussed earlier and configures this on its interface. Again, this address is still in tentative mode at this stage. It performs the duplicate address detection similar to the way it has done duplicate address detection for the linked local address by sending out a neighbor solicitation request. And when there's no response for that particular request, it then transitions that particular address into a preferred state. So we'll now talk about IPv6 support in OpenStack Neutron and how we can create IPv6 subnet. So OpenStack Neutron has support for creating IPv6 subnet and then associate these subnets to Neutron router. Now when you spawn VMs in this network, you will see that the VMs acquire IPv6 addresses and they will be able to communicate to the other VMs and to nodes in the internet using the v6 address that is obtained. So when you're creating a Neutron subnet, there are a couple of parameters. Particularly, I would like to talk about the IPv6 array mode and address mode. In this slide, you'll see that I have captured a screenshot and I have highlighted few parameters. The first one is like IP version, which naturally you have to supply a value of 6 for that. Then depending on the kind of network that you want to configure, you can choose IPv6 array mode and address mode accordingly. So this is a table that will actually give you some example on how you want to, what kind of values you want to provide to the array mode and address mode. The first 3 values are basically used when you want to use a Neutron router or basically an ODL router. Basically that's a virtual router, by the way. So if you want to have a Slack, you supply Slack for both of them on DHCPv6 stateful or stateless accordingly. Slack, it's very straightforward. Everything is obtained in array. And when you use DHCPv6 stateful mode, the prefix information, basically the prefix length is, and the default route is obtained from array. And the guest VMs will talk to the DHCP server, which in the Neutron reference implementation as well as in the OpenDaylight implementation is the DHCP agent. So it actually talks to the DNS masquerade process, and the DNS masquerade process would actually reply back with the address. The last use case here, which I highlighted with a green background, is about a provider network. So here we are actually configuring an array mode as not specified and address mode as Slack. So what it implies is, let's say you have a data center and you have a physical IPv6 router in your data center, and you have a couple of servers there which are already having IPv6 addresses which are obtained from the physical IPv6 router. Now we want to spawn VMs that are able to talk to the other VMs or the bare metal servers. You can create such networks and they are generally called as a provider network. So in this particular configuration, you don't associate these provider networks to any Neutron router. Rather, you specify the same prefix that is actually advertised by the external router, and you also mention the gateway IP accordingly so that the traffic can be appropriately routed to the appropriate physical IPv6 router. So here, guest instances directly obtain IPv6 prefix from the external physical router and then acquire v6 address, and they can talk to other VMs and servers. There are some key differences between IPv6 and IPv4, and I'm not talking here about the protocol level differences. Rather, I'm talking about the Neutron-specific differences between v4 and v6. So you're all familiar with how we are using IPv4 in OpenStack Neutron as well as in OpenDaylight. There are certain differences, and those differences include, first of all, there is no NAT in IPv6. Well, there's no need because we have plethora of IPv6 addresses at our disposal. Likewise, we don't have a floating IP support for IPv6 addresses. The third important point which I'd like to talk about is IPv6 subnets are expected to be created with a global unique address prefix that are externally routable. Now what this implies is, In case of IPv4, when tenants are creating IPv4 subnets, they generally can just give some random subnet CIDR, and that can even overlap with the subnet CIDRs of other tenants. While this is not a problem with IPv4, because when the traffic has to be routed externally, we use the floating IP, or the traffic is actually NATed and then sent out. Since we are not supporting NAT and we are not using floating IPs for IPv6, the expectation is that the subnet CIDRs that are actually used during subnet creation should actually be globally routable, which is very difficult to be expected from a tenant. Now, how do we mitigate this situation is like we have two solutions for this. The very first one is to use the subnet pools, and the second one being the prefix delegation. Prefix delegation is not supported in OpenDaylight as of today, so let's talk about subnet pools. So a subnet pool actually manages a pool of addresses from which subnets can be allocated. What it does is it ensures that there is no overlap between subnets when subnets are allocated from the same pool. So how do we create the subnet pool is like, it's an admin job. The admin would actually create a large pool of subnets, name it as a subnet pool, and then mark it as shared. Now when it does it, tenants, when creating subnets, they can, instead of specifying the subnet CIDR, they can simply specify the subnet pool ID, and a pool of addresses will be pulled out from the subnet pool and then configured onto the subnet. The next one is Neutron only supports EUI64 IP address assignment. Now what is this EUI64 IP address assignment? In the very first slide, we talked about the global unicast address, and we mentioned that there's something called interface ID, which is 64 bits. Now this interface ID is automatically computed by the host, and there are different ways in which this interface ID can be generated. The most popular one is known as EUI64 way of deriving this interface ID. And how is it done is the 48-bit MAC address is converted into a 64-bit interface ID with some standard algorithm, and there's a process for that. That is a standard way, but in some of the modern operating systems, because of some privacy concerns, an alternative mechanism has been devised, and that is known as privacy extensions. So when privacy extensions are used, the interface ID is not computed using the MAC address, but it is actually derived with some random numbers, which is why we do not support that use case. Because what we want, end of the day, is that Neutron should know the IPv6 address configured on the VM so that it can configure the ACL tools accordingly and also program the necessary flows so that the traffic can be appropriately forwarded. Now, if the VMs just configure their own addresses, then it's very difficult for Neutron or OpenDaylight to configure those flows accordingly. The last one is a subtle difference in the way we have, IPv6 addresses configured for router interfaces and all. So we can take it offline. Now, Daya is going to talk about ODL implementation.
Thank you, Sridhar. So thanks for providing an overall view of what the IPv6 protocol, what are the salient features that are relevant to us when we talk about how the implementation has happened in Boron/Carbon, and also how does Neutron look at it, because when you go to a data center environment, there are certain constraints under which you're operating, and we sort of adhere to the same sort of framework that Neutron pushes, right? So we've started the IPv6 activity. I think Sridhar started in Beryllium cycle. It became a part of the mainstream network project as part of the last Boron cycle, and it continues in Carbon. So I'll talk briefly about what we've implemented so far in Boron, and then what is currently going on in Carbon, so that any developers out here who are interested in contributing to this effort are welcome to get more details from us, join us, get an idea of what is the scope of work involved. Okay, so so what is shown here? Where is my pointer? Not working. Okay. Yeah. Okay. So in the yellow block, what you're seeing is primarily that's ODL, right? The northbound orchestration for IPv6, as Sridhar mentioned, comes from OpenStack. Now, in a pure OpenStack environment, there are two ways in which routing or L3 services can be offered. One is you have a separate node which is running a Neutron L3 agent, and that is like a router box, and that is doing all the layer 3 forwarding IPv4 or IPv6 for you. The second one is a distributed DVR type of model, where the routing functionality is distributed across all the switches or layer 2 switches that are part of your Neutron domain. Okay, we follow the second method when OpenStack works with ODL. We, by default, we go with a distributed router model. Now, this distributed routing functionality would not be programmed/influenced by Neutron directly. In the case of an ODL-based deployment, what we do is the SDN controller, ODL, and primarily the component, the L3 component within the network project, would use the southbound plugins, OVSDB and OpenFlow, and they would configure the switches. Primarily, we work with OVS today, but we also have support for hardware VTEP type devices for layer 2 only today. So, so the network component would go ahead and program the necessary flow rules on your OVS switches that are part of all the hypervisors or compute nodes, and that are built. So they build the overlay, they configure all the flows that are needed for your IPv6 SLAC, as well as layer 2 forwarding, as well as layer 3 forwarding. Okay. So the main components of interest to us for this activity are these four. One is an IPv6 control module, and what this does is it enables all the SLAC functionality. It will also provide the RA router advertisements so that VMs can auto-configure, they can do router discovery, and this module will do all the router advertisements that are needed for that component to work. So it's basically the entire control component of the IPv6 protocol that is part of network. The ACL service is what implements security groups. So we've extended the security group support via the ACL service for IPv6, and we'll go into a little bit more detail on that later. The L2 or the ELAN service provides layer 2 connectivity between VMs. So VMs that are in the same network can, when they communicate with each other, the layer 2 service has programmed all the flows that are needed for this communication to happen. And that supports IPv6 as well today. It is a bit agnostic because the layer 2 service primarily works on MAC addresses. So by default, if your IPv6 VM has gotten an address through SLAC, and it has configured, auto-configured its address, two VMs who have auto-configured their addresses to be in the same subnet, with the overlay, the way it is created, they can just automatically sort of start communicating to each other because the layer 2 service doesn't care about IP addresses. It just cares about MACs. And then the next is the layer 3 service, which is actually going to implement the distributed routing across all these vSwitches. A future activity that we want to support is enabling external network connectivity through BGP VPN through VLAN. So we'll go into a little bit more detail on that. So just to sort of qualify where all the IPv6 protocol concepts that Sridhar just talked about, where they fit in this ODL / this deployment, is all the host protocol messages, router solicitation, neighbor solicitation. Those messages would primarily be exchanged between the VMs themselves and the IPv6 control component in network. Okay. All the forwarding rules for layer 2 as well as layer 3 would be between the ELAN service and the L3 service and the OVS switch that resides in the hypervisor of the compute nodes. So what we show is a BRINT. So we create one bridge called BRINT for all the flows that need to be programmed in the switch. Okay, and then for IPv4, we also have SNAT DNAT rules that get forwarded, that get programmed by the L3 service. And all the distributed routing rules, the fib tables, we create fib tables on every virtual switch or OVS for distributed routing. So those get programmed by the L3 service on the BRINT in your vSwitch. And eventually, when we will add the BGP VPN-based support, we will publish some of these prefixes or VM endpoint host routes to like a gateway entity for your data center, so that those can be communicated to the external world, and then you can have communication between external entities and endpoints inside your data center. So any questions at any time, please feel free to ask. You'd like to keep it interactive. If you have any further questions, do interrupt at any time. Okay, so on the southbound, it's a mix of OVSDB and OpenFlow for all the switch programming that we use. And the ACL service is, like I said, going to program some security group-related rules, again on the vSwitch that the VM is connected to. So on sort of the ingress compute node, as well as the egress compute node for a packet path. Okay, so what are some of the services for the control path that we talked about? Let me just go back to this one slide. Actually, let me just start here and then we'll go there. So the messages that Sridhar talked about, neighbor discovery, router advertisements, all of these get supported by the IPv6 service in the controller. And how this works is that, so let's say a VM is sort of ARPing the IPv6 version of ARP, which is neighbor discovery, right? If an IPv6 endpoint sends out a neighbor discovery for a router interface, which is owned by the controller, then the controller will respond to such packets through its control or management connection to the switch to which the host is to which the endpoint is connected. So what we do, if I can go back to this list. I'll just go through what sort of messages are trapped by the controller and what messages are basically sent into the network for a host, right? So let's say the controller is sort of owns the Neutron router for the VM, right? And it wants to be the router to which the VM sends all the packets to. Although the controller itself is not a node in the data path, at least in the OpenFlow implementation, it is giving that distributed router view to all the endpoints. So what happens in this case is, if the VM sends a router solicitation packet, right at the vSwitch in the compute node, that packet is trapped. It is not flooded in the network. The packet is trapped, and an OpenFlow message, out-of-band OpenFlow message goes to the controller. And the controller knows that it is the router for this, and it supplies its own MAC address as a router advertisement message to the VM, so that the data packet that comes in is going to be sent with the controller's MAC address in the network. Okay. Similarly, the controller will also send router advertisements to these VMs. Again, these are not sort of generated by a node in the data path and sent all over the network. These are generated by the controller, sent to each individual compute node where there are any IPv6 endpoints present for this network, and then they are sent to the VMs that are connected to those nodes. So it's a very sort of limited advertisement that is going on for such messages. For neighbor solicitation messages, now these could be for the router interface, or it could be for any other interface in the same subnet. So what we do here is that neighbor solicitation messages are, you send a copy of the packet to the controller if it is the router interface that is being solicited for. If not, then the packet is just flooded in the network. And this flooding, again, because we have an overlay-based implementation, the flooding is not just flooding it on all the links. It is sent to every other endpoint where this network has a footprint, which means if the switch has a single VM belonging to this subnet, then a copy of the packet will be sent to that switch. If it doesn't, then it's not. Okay? So we always keep a list of what are the switches that have a footprint for a given subnet, and we send all the floods to only such entities. So neighbor solicitation messages are flooded. Neighbor advertisements are, again, they're sent in response to these. They can also be, I think, broadcast unsolicited advertisements, right, like GRAT-ups. So those could be flooded, or those could be unicast back to the requester. And redirects, of course, are between routers, so there's no sort of flooding concept involved here. Okay, so let's go back to where we were. Okay, so what we have implemented is that the distributed router that is implemented by the controller will respond to neighbor solicitation messages. It will support periodic router advertisements sent out on the network to all these VMs. And there are all the topology that I mentioned, right, where what is the subnet footprint, what are the endpoints to which I need to send packets to or receive packets from. That entire topology will be maintained by the controller. And it also interfaces with Genius, the Genius framework. There is a tutorial on this later for application coexistence. So, IPv6 service will very happily work by using the Genius framework with all these other services that are part of network, including ACL, L2, L3. There's other services in network like DHCP. So all of these services can cooperate in programming the OpenFlow pipeline using the Genius framework and happily coexist with each other. Okay. All right, so what is the current status of where we are at the end of Boron? Some of this work for Carbon has already started, but I'll just sort of give a status based on where we've sort of finished in Boron. We have finished Slack to a large extent. So basic router advertisement based auto configuration is done. Also stateless and stateful DHCP using a neutron agent. So if you deploy a neutron agent which is supporting DHCP in your network, you can also do stateless as well as stateful DHCP in that deployment. We have implemented layer 2 forwarding. So if, for example, in this diagram, we are showing 2 compute nodes with OVS switches in them. And a VXLAN overlay has been created across all these compute nodes, which is that VXLAN tunnel line down there. You can create VMs. Nova will create VMs as it pleases across that entire overlay, depending on its scheduling and other considerations. And any VM, so VM1, the blue VMs are in the same network, I guess, yeah. And the red VMs are in a different subnet. So we have implemented layer 2 connectivity as well as basic layer 3 connectivity is supported today. So all of these VMs can today talk to each other. So that functionality has been implemented. IPv6 security groups has been implemented. So we do have, we use the OVS contract facility to keep stateful nature of OpenStack security group rules. So we have implemented the same for IPv6 so that the default security group rules have also been implemented, and the user can also create their own rule set and apply to IPv6 endpoints. There is support for anti-spoofing rules. So while we are not as strict as I think the default OpenStack implementation, maybe Sridhar, he's worked on the OpenStack implementation as well. You could maybe give some more details, but we are not today as strict as the neutron restrictions for host-to-host communication. But we do have some amount of anti-spoofing rules to prohibit a VM from using any IP or MAC that has not been allocated to it by Neutron. Okay. And we only support stateful security groups. So just to give some background here, but Ashwin will go into more detail on this in his session. There are 3 ways in which security groups can be implemented in OpenDaylight today. One is called stateless, where you're just using flow rules, basic OVS, open flow support, and you're just sort of saying who can talk to who through flow rules. And that's called stateless. We do use an OVS learn action to optimize it a little bit. The other way is stateful. In stateful, we use the contract module in OVS so that it can keep track of the state and map any reverse rules and create those automatically based on outgoing rules. So that enables us to support stateful security groups to a large extent, as Neutron expects. And the third is a mode called transparent, where you're basically disabling security group rules for that interface. And that is needed for service chaining type of use cases where you don't want, you do want the VNF to process packets, as Anil was talking. If you want to send them through service chains, you do want that VNF to be able to send and receive packets, even though it is not the source or the sink for such packets. So for such connections, we disable the security group rules. And overall in ODL, you can set a transparent mode and just bypass that whole functionality. Okay, so that's where security group rules stands for IPv6. Oh yeah, we've added one more feature where if your VM has VRRP, for example, VRRP has been enabled on your VM endpoint, then we do have support for this functionality called allowed address pair. And what this does is, the VM, when it's booted up, comes up with a given IP, right? And by default, the security groups will only allow the VM to communicate using that IP. But when you configure VRRP, it gets an additional IP, which is shared between that VM and another VM. So by using the allowed address pair API, you're telling security groups to allow the VM to also use the additional IP. So basically, it's a negation of the security group rules for that specific IP. Okay, so that has been added as well in ODL. So there are some minor changes pending to make these rules more aligned with the Neutron restrictions, and we can go, if you meet us later, we can go into those details if anyone is interested. So how, did you want to take this? Or? Okay. So how does the flow actually work on VM boot up? So let's sort of go through the flows here. And one disclaimer is I'm not a coder, so I will try my best to explain the flows to you. But Sridhar, please interrupt me if I misspeak on anything. Yeah. So VM would basically, when it boots up, it would first send the router solicitation message, right? Or it would, upfront receive a router advertisement message and be able to configure its own IP address using Slack. Okay, it uses its MAC address and the subnet prefix that's received in the router advertisement, and just sort of create its own. So that basically enables you plug and play for IPv6, right? You don't have to go into each VM and configure its, if config, IP config. So they've tried to avoid, all those steps using Slack. The other is, I think 133 is, oh, I have 2 more minutes. Okay. The other thing is the DHCP v6 solicitation message and the advertisement. So, as we discussed before, both of these enable the stateless and stateful DHCP. So today we are using a separate Neutron DHCP agent, which will respond to these messages and provide either the address or additional parameters to the VM. Okay, this is a bit tough. Maybe do we want to skip it and or yeah. Security groups we talked about, right? Okay, why don't you, yeah.
Since it's not very clear and since we're running out of time, let's actually quickly wind up. So these are just few slides which we wanted to showcase that the VMs when spawned on east-west in 2 different networks, which is, by the way, dual stack. They can acquire IPv4 as well as IPv6 addresses, and they can communicate with one another. So we're just doing some ping 6 from VM1 to VM2. both of them are on two different compute nodes. So the IPv6 traffic is actually tunneled over the IPv4 transport and sent across the other node. So that use case is supported. This is only a demonstration for that. And in terms of stateful security groups, I'm sure Ashwin is going to cover in detail tomorrow about the security group implementation and how things work. A small caveat which I would like to mention here is that in order to use the connection tracking support for IPv6, you will have to insmode a module which is known as NF-contract IPv6. What we have noticed is in most of the distributions, this particular module is not insmoded by default. So when you start using IPv6 subnets and when you have security groups enabled, please make sure that you have this module already there. So we have some pending activities or like the activities that we intend to take up during the carbon cycle, and they are like the north-south communication, both using the VLAN-based connectivity as well as BGP VPNs, MTU advertisement in router RAs, support for IPv6 provider network use case. There's only some minimal amount of work that needs to be done here. And depending on the resource and time availability, we will take up the other advanced use cases like prefix delegation, underlay, and so on. This is a link to the Google document where we capture the high-level IPv6 design, the current status, gap analysis, and so on. So interested people can actually take a look at it. We meet every Tuesday at around 8:30 p.m. Indian Standard Time, so we welcome people. Please join us, and it'll be fun.
So just one line I'd like to add to what Sridhar has mentioned. The network community is a very large and very diverse community where a lot of, if you check out the Trello board, there's a lot of projects in the pipeline, a lot of new features that we're adding, and we always welcome new contributors. And Anil, Vishal, Sunilu, all of them, Sridhar, they do an excellent job of helping people come on board. We have participation from, I think, about 15 vendors already, so it's very diverse and cooperative community. So we do welcome, if you're interested in working on OpenDaylight, this is an excellent project to get exposure to open source, get help, work with very good community, and also have a good, so we work on an end-to-end solution type of model. So we, all the features work with OpenStack, network, the plugins, different switches. So we look at the whole spectrum. So it's a very good sort of a community to work in if this is where you want to start getting engaged. So do consider it and join the project if you're interested.
So we don't have time, but you can reach us. We are here both today as well as tomorrow. So if you have any questions, we are happy to help. Thank you.
Thank you. So let's get settled in. We want to get started with the session. I think we're already about 5 minutes over. So I'll let Sridhar introduce himself and then we can get started.
Good morning, everyone. My name is Sridhar, and I work for ADAT.
My name is Daya Kamath. I'm from Ericsson, principal engineer there, and I work primarily on the network project that Anil has mentioned in his previous presentation, focusing on a wide variety of features in that project.
So one thing we'd like to mention is that the questions are not just at the end. So if you have any questions, you can interrupt us as we speak. So please raise your hand so that we can take your questions. In case if you feel that the question actually requires more time, or probably if it's slightly out of the context, we can always take it at the end or maybe after the session. So let's start with the agenda. So we'll be briefly covering about some introduction on IPv6, covering neighbor discovery protocol, then going into the Neutron IPv6 support, like particularly from an API point of view, how it's supported. Then Daya will be covering IPv6 support in ODL Boron as well as carbon cycle, how it's implemented, its basic design, and some of the security group stuff and so on. We'll finally leave you with a 16-bit subnet ID. When you have a 16-bit subnet ID, it's like 2 power 16, that is 64K different subnets. So as an end user, when you receive a global routing prefix of /48, you are allowed to have 64K different networks or subnets in your home. They felt that maybe this is kind of redundant and then reduced it to /56. So moving on, here we'll be talking about the neighbor discovery protocol. ICMPv6 plays an important role for neighbor discovery. It is primarily used for some of the use cases like address resolution, duplicate address detection, router discovery, neighbor unreachability detection, and so on. So what is router solicitation? There are basically 5 different packets when it comes to neighbor discovery. The first one is router solicitation. When a host actually comes up and it wants to acquire an IPv6 address using auto configuration, it sends out a router solicitation to see if there is any IPv6 router in the network. The response to this router solicitation is the router advertisement, and that comes from the IPv6 router. So what the router does is it periodically sends out router advertisements, and sometimes on demand basis, when there is a router solicitation request coming from VM, it immediately transmits a router advertisement. It is this particular package conclude with some snapshot on the basic use cases that we are currently supporting, and we'll finally have the roadmap stuff. So this is a slide that shows the IPv6 header. So IPv6 is not just about having a larger address space, but it's actually a protocol that is designed to be more efficient and more optimal. So the basic IPv6 header is of about 40 bytes. One noticeable difference that you can see here is that the number of fields between the IPv4 header as well as IPv6 header is, in IPv6 you'll find less number of fields. And one very visible one is that you don't see a checksum. So the main reason behind actually choosing less number of fields here is to have a more efficient processing by the intermediate routers and also on the nodes. So the fixed header is of 40 bytes, there's no checksum field, and so on. Although the number of fields have been reduced in the header, what it actually has is an optional extension header. So the optional extension header is used on a need basis, and in most of the cases, only the fixed header is used. There are some optional headers like hop-by-hop extension header, routing header, fragmentation header, and so on. So whenever there's a need to fragment a packet, that's when the fragmentation header comes into picture. So that follows the IPv6 header. So the next header field will be pointing to the broadcasting. They kind of use multicast extensively. So even within the unicast addresses, we have different types. The first one is, let's say, the global unicast address. That is like public IPv4 address. Then we have the link local addresses, which are addresses that are used within the local network. We also have unique local addresses, which are like private addresses in IPv4. Let's talk about the global unicast address, because the focus of our presentation is mostly on the IPAM use cases. A 128-bit IPv6 address consists of 2 things. One is the subnet prefix, and the other one is the interface ID. Subnet prefix is usually 64 bits, and the interface ID is 64 bits. Usually, the best practices dictate that you should use a /64 prefix on the end host or VMs. However, on the networking gear like routers and all, you can have a smaller interface ID for some security reasons. So with this 128-bit address, which is split into subnet prefix as well as interface ID, the subnet prefix itself can be divided into 2. When you get a prefix from your ISP or a service provider, he can normally provide you a /48 or let's say /56. During the initial days of IPv6 adoption, they used to give a /48 prefix. Now when you have a /48 prefix, that fragment header and so on. There are 3 basic types of IPv6 addresses. The first one being the unicast address. It's actually an address that is assigned to a single interface. Any packet that is destined to that particular address is delivered to the corresponding interface. Multicast addresses, on the other hand, are very similar to the multicast IPv4 addresses. They represent an IPv6 multicast group. Hosts that are interested in receiving packets destined to that multicast group can join the multicast group, and the routers will make sure that packets coming to that group are forwarded accordingly. We have a third kind of address that is known as the anycast address. This looks very similar to the unicast address, with a slight difference that it's not assigned on a single interface, rather it is assigned on multiple interfaces and usually on different nodes. So when a router has to forward a packet to an anycast address, it looks into its routing table and then looks at the nearest interface to which that packet has to be delivered. Although we have these anycast addresses in IPv6, it's still kind of an experimental stage, and it's not kind of widely deployed. So you can see that we don't have a broadcast address in IPv6. So broadcasting is completely eliminated, and wherever they need